Thank you very much, Andy. I'm really delighted to be here. My first trip to this proper CCQ. I mean, I have been here before when this was all under construction. And, I have known Andy Millis well since 1990. We wrote several papers together in the 90s. And he's one of the persons I respect the most in the world. I mean, it's with no I don't exaggerate. This is just the truth. But I did not know this side of Andy. The reason I liked him very much, he's no nonsense, says things as it is. I don't know that he's capable of flattering. Okay, this is like I'm seeing a new side of Andy Millis. Maybe as we get older, we develop abilities that we didn't have. Thank you very much, Andy. All right. So what I want to talk about is.
I'm sorry. Now that you started, let me just interrupt to say very briefly: A, that Sankar has graciously agreed to take questions during the talk as well as at the end. Yeah. And B, if you're watching the talk on Zoom, put your questions in the Q&A or in the chat, and I will raise them with Sankar as appropriate. Sorry.
Yeah, and I'm here all day. Feel free to find me, talk to me, or make an appointment, and then you can send me email. I mean, I basically do physics 168 hours. I have nothing else in my life. So I'll be very happy to communicate with any of you. So the subject I want to talk about is, I would say, one of the most active areas in all of physics, and I don't think I'm exaggerating. Graphene has turned out to be a superconductor, not monolayer, really boring graphene, but certain aspects of it, like twisted graphene, but even untwisted graphene. As most of you know, I'm going to talk about it. And this work is one of the few works which is entirely within CMTC. As Andy said, we have a very, very active center. I mean, 15 postdocs and 15 students and only 3 faculty members. It's a very coherent center where we do things together, collaborate a lot. And so it's Jaideep Sao is one of my colleagues who's involved a little bit. But the main work is Yangzi Chao's main work I'll talk about is Yangzi Chao's. And we just posted a paper, I think this Monday, which is like a 25-page paper where many of the things I'll be talking about will be there. And this is our first paper. This paper took almost 2 years to get accepted. Reason is that we said it's electron-phonon interaction. And of course, nobody likes electron-phonon interaction because, because 99.99999% of superconductors are caused by electron-phonon interactions. If you see electron-phonon interaction, experimentalists don't like you because it's novel enough. Theories don't like you because they think it's boring. So we had great difficulty having the paper published. But I think that, okay, let me give you my opinion. I think all the superconductor is graphene arising from electron-phonon interaction, with one exception that I'll talk about. And not everything is completely understood. I'm not claiming that, but I think we understand quite a bit. Okay. So I also have extensive discussion with Andrea and Pablo, and recently with Andre Bernovic, and we have started a collaboration with Andre on extending some of this work to make new predictions, actually. Okay, so this is the famous original experiment, Kao et al. From MIT, which started the field. And what the group found is that if you take 2 layers of graphene, 2 just layers of carbon in hexagon, and twist them with respect to each other so as to make the unit cell very large. I mean, the fact that it can be done is amazing. It sounds like science fiction, but when you do it and look at the system, you find a plethora of what looks like exotic phases. There is an insulator. I mean, never mind whether it's Mott or not, there is an insulator at some filling. There is superconductivity, other places, electrons and holes, both sides. And and there are all kinds of properties of these systems, magnetism, Chern number, valley polarization, which could all be big subjects. I have written a lot of papers on this, but I will focus on superconductivity. Okay. And I'll tell you a bias right in the beginning. My bias is that this system would have been superconducting everywhere, but it's preempted by all these strongly correlated phases at certain fillings. And these 2 physics are independent of each other. If you take aluminum, it's superconductor, but it also has many other things, and the superconducting part, I believe, comes from phonons. And, I'm just telling you my belief, and we have calculations supporting it. Questions can be raised, of course, it's a difficult system. When you say electron-phonon interaction, and you are a theorist, you have a tremendous disadvantage. because then you have to produce all the numbers that agree with experiment. People think that, oh, electron-phonon interaction, everything is known. It's not true, everything is known. If you say electron-electron interaction, nothing is expected of you, because no calculation can be done. You just throw the word strong correlation randomly here and there and talk about exotic stuff, because people know calculations are very hard. So this is the reason we face problems with referees. It drives me crazy, but that's the way science goes. So there was a very important experiment from Spain, Barcelona, Efetov, a graduate of a very famous university that I'm sure Andy will agree with me, okay? So Efetov got his PhD at Columbia. So what he found, this experiment is pretty amazing. What he found is that there is this huge superconducting is basically like everywhere. And then there are, at commensurate filling, there is insulating phase. This experiment was very instrumental in developing my intuition for it. In fact, this was presented at a KITP conference. And I immediately said that I think this is telling us that it's all superconducting, except superconducting phase is preempted by strong correlation and insulating phases. But since we are theorists, I had to do some RG calculation showing that we can actually calculate electron-electron interaction in this superconductivity. When you do RG in a complicated system, you find superconductivity everywhere. This is a very formidable RG. I mean, we have a postdoc, Robert Throckmorton, who, I said the full RG is impossible. It's 34 parameter RG. Basically, people do 1 or 2 parameter. With symmetry, could reduce to 10, but this is really a 10 parameter momentum shell RG. And what he found is that almost every phase you could think of, there will be a phase transition, there could be, this is the problem with RG. It tells you what is possible, doesn't tell you what actually happens. It's a contact electron interaction, but we found lots and lots of fragile states, which I think is consistent with the experiment. No two samples show exactly the same phase diagram. There are many, many phases, and most of those phases, all of those phases are coming from electron-electron interaction, okay? And the superconductivity is invariably some high orbital superconductivity, which is what we expect from. I'm not going to talk about this. This is just to say that it's not like we ignored electron-electron interaction completely. We did the calculation that everybody else does, in our own language, and we found topological superconductivity. We found, all kind of density waves and the superconductivity P and D. But I do not think that these finding of ours, and there are many, many papers like this in the literature. They're all very nice theoretical papers. But I think TC for all these superconductivity is very, very low. And I do not believe the superconductivity that is observed in any of the graphene samples has anything to do with these RG calculations. This is a strong statement, but among experts, I do not want to kind of be wishy-washy. That doesn't help. If I say it could be this, that could be that, well, then at my age, that makes no sense. I'm going to take stands, okay? So, these Morris systems are flat band systems, right? We have make the unit cell very large, so the system has very flat band now. People thought about flat bands for a long time. I have a paper. This is when, I think this is even before Jennifer Cano was at Santa Barbara. This is, this is a long time ago. I was running a program for 6 months, and we had a paper on flat bands. In fact, it was honeycomb lattice. This was, we were very we were not bold. We said, oh, maybe they can make it in cold atoms. These are the days when we thought cold atoms can do everything. Okay. And now I was going to make a comment, but I'm going to be on YouTube. I'm not going to make that comment. So these are the days when I thought cold atoms could do everything. And we wrote this paper, flat band, it's an analytical work showing that all kinds of Wigner crystallization comes up. Then there was another paper we wrote, which is trying to create quantum Hall effect with again, flat band. And the very famous paper, most of you know that, is Alan McDonald wrote a paper in twisted double layer graphene. This is now called twisted bilayer graphene, showing that there will be these flat bands. Now, why am I showing this paper? Not to brag that we thought about it a long time ago. I have to emphasize how limited our imagination was. What did we predict after all this? All of these 3 papers? Oh, there could be Wigner crystallization. That is where our imagination ended. All of these 3 papers in the end just said Wigner crystallization. Okay. Not a single one said there could be superconductivity. Okay. All these 3 papers have quotations from here. So this again tells me, of course, you're not thinking about electron-phonon interaction. You're thinking just of electron-electron interaction. So you could think of ferromagnetism, antiferromagnetism, Wigner crystallization charge density wave, but did not think of superconductivity. So all three papers speculated the most exciting flat bank possibility non-predict superconductivity. Okay, this is just a fact. You can go look at these papers. So are there concrete established examples of repulsive electron-lepton interaction in the superconductivity? Concrete. I'm going to make a strong statement, and I'm hoping that Andy will challenge me. My answer is no. There is no concrete example. Helium-3 doesn't count because helium-3 first is not a superconductor, superfluid, and the issue of phonon. I mean, those are some kind of spin excitations which come from electron interaction. So one mechanism, of course, which probably all metals go, eventually become, if you do RG, you find that at some low T, very, very low, exponentially low, it becomes superconductor, but I do not think that shows up in, what that number is. I mean, this number is variable. It could be, as high as even 1 microkelvin in some case, but I do not think that anybody has ever come up with a Kohn-Luttinger higher than microkelvin. And this is high orbital pairing, non-S wave. And it basically arises from Friedel oscillation, that you have electrons, then there's Friedel oscillations. So you have some attraction in some high channel, and that would produce superconductivity. But since the interaction is mostly repulsive, the TC is very low. So I would claim, again, I want to make strong statements so that we have discussion and disagreement. I would say this is no experimental, it has no experimental relevance, and I want to be corrected. And strong coupling analog of Kohn-Luttinger, people have looked for it. I know Steve Kivelson looked for it a lot. Maybe Andy did also. I do not know of any example. I think minimal Hubbard model does not manifest any strong coupling superconductivity. This is not my work. I do not do quantum Monte Carlo, but this comes from my quantum Monte Carlo guru, Matthias Treuer, who told me that there is no evidence. It doesn't rule it out, but yeah.
So you're restricting to theory here?
Yeah.
Okay. So
everything is theory here.
Okay. So we can't say like an experimental heavy fermion materials, for example.
No, I'll come to heavy fermion material. First, heavy fermion material. I'm defining electron interaction in a specific manner. Okay. If you're exchanging a spin excitation, to me that's just like regular BCS theory. It arises from electron-lepton interaction, but I'm talking about direct electron interaction. It's a bit semantics. Okay. So that's why I said helium-3 doesn't count. So heavy fermion is like that. But I do not know how definitive the proof is that those are not electron phonon. I'm not a heavy fermion expert. Is it definitively established it's not electron phonon?
You're probably just looking to the spin wave velocity has been measured.
Yeah.
Orders of magnitude below the sound velocity.
Okay. But I'm definitely making a distinction. Yeah, I'm definitely making a distinction that if you are exchanging some, magnons or something like that's really like a phonon. The fact that they comes from originally from electron interaction is not very. Yeah. Yeah. Right. Yeah. And people can have weak coupling. So the basic thing is very simple. Coulomb interaction is repulsive, and it leads to the famous mu effect, which suppresses superconductivity. But there could be situations. This is an open question in condensed matter physics. I'm not ruling out that this can never happen. I'm saying the cases I looked at cannot be relevant to graphene. That's all I'm saying, because just knowing at 0 temperature of superconductivity is not enough. You have to be able to predict that TC could be a few Kelvin, as experiment sees. Okay. So this is all I'm going to say about electron-lepton interaction.
So may I say, I don't think that this is directly germane to your point.
Yes.
But, I think that recent work by Prokofiev, Svistunov, Halle, probably Kuhn was involved, say that the Kohn-Luttinger picture is not at all correct, and that you can get rather higher, although maybe not high enough for Moray materials, TC from what boils down to exchange of plasmons. So
yeah, this I have to say, yeah, I have to say that having written more paper on plasmons than anybody dead or alive, okay, I completely disagree. I don't believe this. Okay, I just do not believe this. That if you include vortex correction, that TC is going to keep on going down. This is what I predict, because there is no Migdal theorem.
No, but their claim is that has been done systematically by the methods of diagrammatic Monte Carlo.
Okay.
So that's
okay. So
perhaps off the topic of this.
Yeah, I mean, it's the last Monte Carlo, the last resort of all scoundrels. I cannot say anything. It's a black box producing some results. Yeah.
So basically,
We find one that does that.
Okay, we should discuss it because I don't believe it. Okay.
so basically, the claim is in the weak coupling limit where RPA is controlled. we show there is a mechanism like a million times stronger than conventional mechanism. It drives to this.
These sort of claims have been made many times. Some of them before you were born. Okay? No, I'm not making it up. I have been around for a very long time. Plasmon is my favorite object in the world. I mean, I love plasmons than anybody else, and next to my children, I love plasmons the most, okay? So if plasmons could produce superconductivity, I will throw a big party, invite all of you, okay? But Jerry Mahan wrote a paper saying plasmons give rise to superconductivity, and then Rusham did a calculation including vortex. That has nothing to do with your work, showing that it goes away the moment you include vortex correction. What I'm trying to say, I understand you have a claim, but I want you to understand what I'm saying. I don't believe the claim, is what I'm saying, okay? And that's my prerogative. I mean, what are you arguing about, okay? You have a calculation showing it. I said, I do not believe plasmons can give TC, which is relevant to any, but we should talk, okay? Maybe you can make me believe, then I'm going to throw a big party. I love plasmons, as you know. I mean, that's our logo, CMTC logo, is the ring diagrams, okay? This is published, right? This is not archived. Okay, good. We should discuss. All right. So I have said everything I'm going to say about electron-phonon interaction, okay? So I'll claim, I think nobody can disagree with this claim. Essentially, all known superconductors by essentially, actually I didn't have essentially, then I realized Andy will be in the audience, so I put essentially, okay? Some exception could be triplet superconductivity, but these are rare, helium-3, and heavy fermion is in this category. I just ran out of space, so I didn't put heavy fermions, okay? Graphene electron-phonon interaction is very weak. We actually looked at what, if you just take a monolayer graphene, at what temperature you expect electron-phonon interaction? It's way below 1 millikelvin. I mean, so it doesn't happen. Electron-phonon interaction is very weak.
Excuse me.
Yes.
So when you say all known superconductors are phonon mediated, you're also anything that's magnon mediated, boson mediated is in.
No, that's in the next line. Okay, some triplet superconductor could be because of spin exchange type of thing, helium-3, heavy fermion, and so on. Yeah, is that your question?
No, but I was thinking more about the cuprates, for example. I understand that no one understands theoretically what's happening, but it's believed that the spin fluctuation mediated.
Okay, I believe it's phonons, but since nothing is understood, this is this is an argument on how many angels can fit on a pin. So
yeah, fair enough.
I mean, everybody thinks cuprates in electron interaction, because everybody wants it to be electron interaction. Otherwise, it's so boring, So that's where you'll find no theoretical paper, no, let's say, no theoretical paper that people respect in cuprate talks about TC at all. So typically, people will give a very fancy talk on, pseudo gap this, pseudo gap that, hidden quantum criticality, and all this. So what about TC? And the person would look at me like I'm some kind of an idiot. Okay, and I would say, but the whole reason people got interested in this subject is high TC. And answer is I have nothing to say about TC. So.
Right.
You are right.
Again, I think our belief is that over a fair amount of the phase diagram, the superconductivity is in the pure Hubbard model is preempted by other phases like stripe phases.
Absolutely. This I agree.
Various people, including me in the manual, have published papers which actually have calculations of TC in the Hubbard model.
And what is the value? So why is Matthias telling me that there is no TC?
I'm not going to speak for Matthias.
Okay.
Except that the phase
so what is the value of TC? That's the question.
If you translate using hopping parameter T, about 150 Kelvin.
150 Kelvin? Okay, I stand corrected then. So I have to ask Matthias, why is he giving me wrong information?
Well, again, I suspect that part of the issue, this goes back to work that Xue and others have done, is that the superconducting state, which is found, is preempted by another phase, which doesn't show up very well.
Yeah, but Hubbard model applies to many systems, not just to cuprates. Why isn't superconductivity everywhere?
Well, I mean, as I said, there are stripe phases and things like that have to be.
Okay, so this is a good discussion, and we should have it. Since I have nothing to say about it, it's I don't disagree with this, obviously, but this is not what is going on in graphene, I think. At least nobody has shown it. So why is electron-phonon interaction graphene important at all? Okay, because in real graphene, just monolayer, TC is very low, as I told you. What happens in Morris system, and this was really the only insight I've had, because Andrea Young called me and asked me why their resistivity is so large, 1,000 times larger than monolayer graphene, and it's linear. I said, oh, it's very simple. Fermi velocity is strongly suppressed. That increases the effective electron-phonon coupling, because that goes into the denominator of the effective coupling. So if you have Fermi velocity factor of 100 lower, Well, electron phonon coupling will be a factor of 100 higher. And in fact, Fermi velocity is 0 at, totally at the point where you have this magic angle, then this coupling is going to go to infinity. Of course, the theory would not apply there. And this may lead to, if you just do a BCS theory without doing anything, just BCS formula, this will immediately give you an SC of TC1K. This is the basic idea, okay? Now, since you have symmetry, I'm going to talk about it, including valleys, you can have higher order pairing. Normally, electron phonon interaction just gives S wave. But here, as I'll show you, there could be degeneracy between S wave and F wave. And so original argument was you cannot get higher order superconductivity, but now we know that that's happens, okay? So it's a candidate. So let's see, just saying it's candidate, and this question came up. So my current belief is that there are some situations, I'll tell you, in particular, Bernal bilayer graphene, it probably is electron paramagnon, but rest are electron phonon. I'm not very happy with that. Two mechanisms come in. If two comes in, it's possible others come in also. So the question is open. I want to distinguish between what I believe and what I can show. What I believe is almost all electron phonon. But what we can show is definitely there is one example, Bernal bilayer graphene, where electron phonon doesn't explain the superconductivity, but electron paramagnon does. So there is still a lot to do. And now, based on what Andy just said, I cannot rule out Hubbard model physics either. I mean, we don't do quantum Monte Carlo, so I cannot do the calculation. But this then should be looked into, over here where you have the facilities and the ability. So recently, several papers have come out. This is one paper. What they do, they take this graphene and you have gates on two sides. And this was an early suggestion. If you now apply gate potential to increase or decrease screening, for example, you can put the gates very far from each other, or you can bring them very close to each other, or you can apply electric field. So if it's electron-electron interaction generated, then when you reduce screening, then superconductivity should be enhanced. When you increase screening, superconductivity should disappear. Well, exactly opposite happened. So this is one paper. So I'm just quoting from the abstract. Although both superconducting and correlated insulating behaviors are strongest near the flat band condition, superconductivity survives to larger detuning of the angle. Our observations are consistent with a competing phase picture in which insulator superconductor. And this is what I was saying, and this is what Andy was saying, what happens in cuprates, that superconductivity is preempted by correlated insulator. If you go to large angle, superconductivity survives and becomes much bigger. But there is direct experiment from the group of Lee at Brown, where he really changed the gate distance in several samples. And so what he found is weakening the interaction strengthens superconductivity, consistent with scenarios in which electron phonon coupling competes against Coulomb interstability. Now, this paper is an interesting history. First posting of this paper, if you go to archive and look at the first posting, it came to exactly the opposite conclusion. Their conclusion was that is electron. They found that TC is enhanced when screening goes down. Okay. And then they found a mistake. I think Andrea or somebody pointed it out. They found a mistake in their measurement. And they rewrote the whole paper with new data. And then it was accepted. And then this is this conclusion. I still remember Andrea calling me and saying, look, they have found this, so I should look into it. And now this is the conclusion. And then Dima Fetaf's group also said the same thing. Our suggests re-examination of often assumed parent and child relation between insulating superconducting phase and Moire graphene. And basically saying that they may not be connected. Of course, he doesn't say it's electron phonon, but he said they may be from different causes. Okay. Now, all these things came 2 years after we have already proposed superconductivity from phonon. So it's not like these papers motivated us. We were, so there are no papers from Lee group. Nature Physics says a possible scenario that electron phonon coupling stabilizes superconducting phase with a spin triplet value singlet order parameter. This is what we said could happen. People originally thought you cannot get triplet superconductivity in the spin channel from electron phonon, but here you can. So, so our paper was posted long before. So I'll make a prediction based on this, since, we are all interested in whether Moire TMD, which is a Hubbard model also, I'll make a prediction here that nobody will see superconductivity in Moire TMD, okay? And, if Andy is correct, his Hubbard model, Moire TMD should have superconductivity. Electron phonon coupling is very weak because I asked in phi, but details matter, as he said. So maybe the calculation in Moire would show there is a superconductivity, but my prediction is this, because I asked in phi math, it is very difficult to find electron phonon coupling constant for this Moire, the TMD materials. I could not find them anywhere. So he referred me to some obscure material science journal where somebody has tabulated. It's incredibly small.
Are the TMDs much more disordered than the graphene layers?
Yeah, more disordered also. That's absolutely true. Yeah, that's absolutely true. But I'm saying even if they're not disordered, I mean, it's going to be like 1 millikelvin or something like that. But again, if they see robust superconductivity, then cannot be electron phonon, then it becomes very interesting. Okay, so this is what I was telling you that, I just gave you the punchline. So 7 nanometers stronger screening and only superconductivity survives, okay? And then when you go to 12.5 nanometer weaker screening, correlated insulator phases comes out, okay? So this is kind of like, you can say some evidence that it cannot be regular electron-electron. So these are the papers that I read from the abstract already. Okay?
The cluster dynamical mean field picture of superconductivity in the Hubbard model is exactly this.
Okay.
You reduce the U to less than if U is greater than the critical value for the Mach transition, you get correlated insulator phases with superconductivity adjacent. As you reduce the scale through the Mach transition, once you go below the Mach critical value, you get a superconductivity phase.
Yeah, so I would say,
again, whether it's
I would say that,
the Hubbard model is
right. Yeah, but the statement Hubbard model is just too generic for me. I would say that this calculation should be done for graphene. The calculations that you did, literally for graphene, exactly, with the full band structure kind of thing, which is what I'll show you. And let's see what it is. I don't think you'll find superconductivity, but I will be delighted if I'm corrected. Trust me, that's what I want, okay? Electron phonon problem is solved, and I would say it should be done. You guys have all the ability to do it. I'm willing to collaborate with you with the condition my name should not appear on the paper, okay? Because I just want to know what's going on, okay? But I do not think it's going to happen, but this is a very good question. This is why we travel and give talks, okay? This is, I'm very excited. And these calculations, a lot of people have used Hubbard model here. So it can be easily adapted to the actual band structure and the calculation can be done. Oops. All right, so I'm going to go back to long time ago, almost 15 years ago, and talk about graphene electron phonon interaction first, okay? So, so we actually did the acoustic phonon calculation. This is another paper. It took like 2 years to get published. And then they did an experiment which agreed exactly with our theoretical paper. This is what we did. We just calculated, did a first principles calculation of resistivity in graphene and TC in graphene, monolayer graphene, because of electron phonon deformation potential coupling. And you get the standard answer that you expect, that at high temperature. But this high temperature, this is not Debye temperature. Often people in books use say Debye temperature. It's not Debye temperature. It's either Debye temperature or Blok-Gruneisen temperature, whichever is higher, whichever is smaller. Okay. And in metals, Debye temperature is much smaller than Blok-Gruneisen temperature because Fermi momentum is so high. But in graphene, it's really Blok-Gruneisen temperature. Blok-Gruneisen temperature is nothing other than this quantity. It's the energy of a phonon with 2 kF scattering, because the most dominant resistive scattering is electron going in this direction reverses its path. So that's 2 kF. So that's the most dominant scattering, and that's the temperature scale. So we should see this. We made this prediction and produced results using the known and this is their experiment. I'll just leave it saying it agrees quantitatively with this theory. And so we get some estimate of the deformation potential coupling is, I think it's a order of 30 electron volt. And then when you put the 30 electron volt, you get a lambda, which is very, very small. This lambda is a dimensionless effective electron phonon coupling that comes here to the theory of superconductivity, made famous by great late Macmillan. And this is essentially zero. It's 100 microkelvin or 50 microkelvin, something like that. Now you can get superconductivity. There's a very good paper by Chubukov and Rahul Nandkishore and Levitov, where the idea was that if you can push the density all the way to the Van Hoff singularity of real graphene, which is almost 10⁻15 per square centimeter doping, then you'll get superconductivity. And there is an interesting story about this paper. In fact, that's what Efetov's thesis was supposed to be. He was supposed to dope graphene to the actual Van Hoff singularity of graphene and see superconductivity coming from electron-electron interaction. But what happened, they could not dope that high. They could only go to 10⁻14. And then Philip saw our paper and called me and I said, we cannot go all the way there, but maybe we can see this T4 behavior, which nobody has ever seen clearly. You know, the Bloch-Bruneisan behavior T4, you cannot really see in regular metals. It's very difficult to see. Since our density is very high, this temperature is pretty high. It's of the order of 50 Kelvin, 100 Kelvin. So you can clearly see it's going from linear in T to the power 4. So they, you know, very smart experimentalists, they snatched victory from the jaws of defeat. They did not see super. This is a very highly cited paper because now phonons are very important. So we know everything about graphene.
Can I ask a question?
Right. Yeah.
Because what's plotted is delta rho, right?
Yeah,
So
yeah.
presumably there's a residual.
Right.
Right. And so there's a question of how big is the temperature dependent part of the resistivity in comparison to the residual.
Yeah.
And the related question is just how does disorder play with the Bloch-Bruneisan effect?
Yeah. So very good question. These are of course things I have studied at great length. It just so happens that this is after graphene has already become very, very clean. So this issue, I don't remember the residual resistivity, it's but minuscule. Okay, so this issue doesn't apply here, but this is very important in semiconductor. And by the way, this interplay can give you all kind of non-monotonicity. Okay, and we have many papers doing that, and these kind of things have been seen in holes in gallium arsenide and so on, because as you know, there could be linear in T dependence coming from disorder, and it's very interesting. And these things in gallium arsenide is reasonably well established. In graphene, disorder due to temperature dependence is not there because it doesn't have the Fermi surface anomaly because it's Dirac. Okay, so 2K disorder scattering doesn't have strong temperature dependence. It's not important. I don't remember the residual resistivity, but it was not an issue because Philip, of course, you know. But it's a good question. Okay, in some other materials, it could matter. So now we need to take that graphene and convert into twisted bilayer graphene. So twisted bilayer graphene, this is the picture. And basically, we use the band structure, same band structure everybody uses. This is the McDonald band structure. And this is a calculation of the graphene velocity, graphene Fermi velocity, as a function of the twist angle. This is this famous magic angle. This is the famous magic angle where in this zeroth order theory, the velocity goes to 0. Okay. Now, this is the Fermi velocity of graphene. This is the phonon velocity of graphene. So I will do a theory which would not be valid over here because, you know, Migdal's approximation will fail when the velocity is lower. But I have a theory which is reasonable over here. Monolayer graphene is somewhere up here, okay, way up, okay, like 5 degrees or something. And there are all these symmetries that we're taking. I'll come to symmetry later on. Depending on the twist, the velocity could be suppressed by a factor of 100. This is the important thing you need to remember. And then we first calculated, our paper is mainly first on resistivity, because this is the question Andrea Young asked me. I actually did not want to get into twisted bilayer graphene because I was late. I was going through a huge personal crisis and could not think of anything new. But since he called me, I knew immediately. I mean, literally, I finished the calculation that evening that he called me. And I could just immediately get resistivity as a function of twist angle. All that is coming in is this. This is basically this formula recycled, doing the full calculation in between, recycled now with Bistriza-McDonald band structure for graphene velocity. So as you can see on this plot, the monolayer graphene will be basically along the horizontal axis. And as the angle goes down, resistivity should go up enormously. Okay. And d rho dt should show this huge change, 100 to all the way 1 ohm per Kelvin, as you go from small twist angle, let's say 1.1 degree, at magic angle in our theory diverges to regular graphene. Okay. And this agreed remarkably with the experiment. Okay.
Right, so can you say which phonon?
I should have said that. Everything that I'll tell you about is just regular acoustic phonon in the layer. Okay, we take into account coupling between the two layers, that doesn't change anything. There is no optical phonon in our theory. Alan McDonald has a paper claiming optical phonon gives a superconductivity, but I would say that Alan himself doesn't believe that, and Fengcheng Wu, who did the work, who came to me, in fact, I did not talk about superconductivity. I thought that obviously they used acoustic phonons. I didn't read the paper, but the optical phonon. Optical phonon doesn't contribute anything.
Sure, but then there was all this other discussion of phonons associated with twisting and reading and
correct.
This and that. So
correct. We have looked into some of those effects. These are some of the things that that Andre and Binlea talked about. We looked into some. We had extensive discussions with them. Some of those physics is included. Main thing is that if because of zone folding, huge gaps open up in the phonon spectrum, then there will be changes in this theory, but there is no evidence that happens, okay? So it seems that twisting has a strong effect on electronic spectrum and not such a strong effect on phonons.
Nor on
Experiment.
the electron phonon coupling.
Electron phonon coupling goes up in the simple theory because a V phonon comes in the
But
bottom.
there's no effect
Oh,
beyond
no,
that because
No,
of
no.
the phonon
You bring up a very good point. D, the basic deformation potential coupling most likely changes. And I'll come to that when I talk about superconductivity, okay? Because I don't know if you know, this deformation potential coupling, which basically means if you apply pressure, how much the bands change, it's not known even for a material like silicon or gallium arsenide very well. Okay, experiments. So it's often set by comparing with transport experiments. And Andy, answering the question, we do need larger value of D than what it is for monolayer graphene. And this is the open question. Some first principles person here perhaps can do this calculation. And referees bring up this question, and it's a justified question, but I'm talking about it. Okay.
Can you just comment or clarify why optical phonons are not important at all? You said
High energy. Optical phonon. Yeah.
But there are many situations when the optical, I mean, not in BCS or not in MIGDAL, if the phonon energy is larger than the Fermi energy, but if it's lower, it doesn't have to be acoustic.
Yeah.
Right?
No, here we looked into it carefully, just doesn't contribute. It's not like I discarded them without considering them. They come into play when I talk about untwisted structures. We include that, and sometimes that enhances TC slightly. Okay. So we have included them in some of the situations.
Okay. And I have another small question. Your theory in principle would not work at the magic angle, right? Because
or even close to it. Our theory, let me go back. This is a very important issue. So I want to emphasize, I do not want to say anything. I don't want to exaggerate, okay? Our theory really doesn't work beyond this point at all.
Okay.
But even close to this point, you can say our theory probably doesn't work very well, okay?
So do you speculate about what's going to happen there, or you?
No.
You
I think what happens is that, I mean, look, the thing is that usually a theory doesn't fail just because somebody's theorem did not apply, right? I mean, if you look at normal metals, there is a small coupling parameter, RS is 7.
Yeah.
But if you do a calculation leading order, dynamical screening, so-called GW approximation, you produce everything well. If there is no phase transition, things do not just go haywire in 1 second. So I believe our theory applies, but I can't make this claim. So results I'll show you, I'll stay above this point, okay? If you answer to your question, I believe nothing changes, okay?
Thanks.
So, Andrea was very happy, and he actually wrote a Nature Physics saying electron phonon coupling induced enhancement in resistivity, okay? So it agrees reasonably well, and let me just go back. So this is data then from Pablo's group. They had a competing paper at the same time, resistivity. And this is our theory, and we found it agrees, but I don't think this group agrees with us. They interpreted a strange metal, everything unknown. Where it's coming from, we don't know. And I think that I'm going to come back to that. This issue is not completely resolved. Meaning, what I'm saying, and since I'm going to talk about superconductivity, we wrote a recent paper where we looked at this question very carefully because of some new data FETAV has published, very careful temperature-dependent data, really, really careful temperature-dependent data. So we got the data from them and used actual numbers and did our electron phonon calculation very carefully. And what I'm confident is that all the linearity they see above 10 Kelvin is coming from electron phonon interaction. But sometimes they see linearity. Look at this. The linearity goes all the way down to like 100 millikelvin. Within our theory, that's very difficult to explain. But we are not doing a full calculation, including the whole band structure and how the Van Hoff singularity moves around. Very kind of things really should be done here. We are not very good in doing it. This work is very slow. But it looks like we can extend it from 10K down to maybe, even 500 millikelvin. But there is a question, if the linearity goes all the way to 50 millikelvin, something else may be going on. And then that brings up the old question that is very familiar to the older people here, Andy and I, that in cuprates, it's linear sometimes, not always, sometimes over a very large range. And some of it could be electron phonon, but at very low temperatures, unlikely to be electron phonon. Then why is the linearity always the same? Why should two different mechanisms conspire to give you the same slope? So there may be a mystery here. I don't want to undermine the importance that our theory typically does not give linearity going below 10K because that depends on Bloch-Grunheisen temperature. Okay.
Actually, the
Is that really linear? It seems like it's curving down.
Oh, when you go to high temperature, what happens is that it actually comes down, because then that's totally understood. That's because electrons are excited to higher bands and so on. Our theory includes those things. Okay? So above, you cannot really take above 50K, it comes down actually. Okay, because electrons are going to some other band.
So I just want to internalize something.
Yeah.
So you have less than 3 decades of a power law. I would just say it's just a curve. It's linear to the naked eye, but it's not really a linear in the critical.
Have you seen linearity in any solid state system, which is more than 3 decades? I haven't.
Yeah, so I don't make a big deal out of it.
Yeah, so I mean, I'm saying that this is a statement, but then there is no scaling anything in solid state physics at all.
No,
Nobody should.
The magnitude is kind of interesting. Is it too like the issue? I wasn't around, but like the issues of resistivity saturation versus non-saturation, for instance.
Yeah, this
What's
is.
the mean free path there? If it's
It's very long. Very long. This is what you are thinking about would happen.
It's consistent.
Yeah, it's all consistent. Yeah, totally consistent. Yeah, absolutely. All I'm saying is low temperature, I cannot claim electron phonon interaction explains the linearity completely. That's all I'm saying. Okay. Over here, I think even Pablo agrees that, but then I have a problem. Suppose there is a mechanism here and there's some totally different mechanism here. I don't see any reason linearity should be. And this question, by the way, this is why I have not written a paper saying in Q-phase linearity comes from electron phonon, because I know I cannot explain the whole region. So, but this would be everybody's problem. So something is going on we don't understand. Okay.
So may I ask 2 questions?
Please, please.
So the first is the different color curves in the experiment.
Yes.
Correspond to densities, as I understand it.
Yes, this
from
is
1.2
right.
to 1.9.
Correct.
Roughly.
Correct.
Okay, and so if I sit at a fixed temperature,
Yes.
there's a substantial change
Yes.
in the resistivity as a function of
Yes.
density.
Yes.
Where does that come from? Because if I look at the theory calculations, right, the change is much smaller.
No.
Right.
This is all shifted.
The middle thing, right?
Yeah, this is all shifted with respect to each other.
Are you sure?
Yeah, because to show them, trust me, this kind of. Let me show you direct comparison. Okay, let's go there. Okay, let me just go there. I have the direct comparison. This is the summary of the results. This is so. What we plot here is d rho dt as a function of twist angle. This is data, okay, as a function of twist angle. These are the data from from Santa Barbara group. Okay, this is the Columbia UCSB collaboration. And as you can see, this question came up. When you are far away, we kind of explain well, but when you go close, this is, and so this is the original theory with the original D, where the value is given. Okay. To get agreement, and this is what I was telling, get agreement, you have to shift it, get agreement over the whole thing. If we shift it a little bit, the agreement improves. That means we need larger D by about 25%. This is what I was telling you, okay? The other possible theory is not very accurate, you should not do this, but we give this plot to give an idea to what extent D changes, okay? So, and you can see this point, there the theory doesn't work at all. So, and the density dependence is very weak, okay? It really is, okay? I mean, it's what the theory says, okay? So it's flat band enhanced electron phonon coupling. And if you estimate, if you take the Macmillan formula, put lambda, you find lambda now has become 1. So from 0.01, it has become 100 times higher, and it goes into exponential. So now just simple theory, which is what our original paper had, TC is 1K. Okay. And this is the part Rafael in light.
Can I ask you this?
Yeah.
How does an experiment TC or superconductivity depend on the density of the carriers?
Well, I already showed you what doping. It depends on the doping. So at some dopings there is no superconductivity, some doping there is superconductivity.
But generally, should I think about the density of the carriers to be small when there's superconductivity, or it can be
sample too?
It depends on sample. Very small, there is disorder. So because very close to the cone. Basically, in our picture, this picture, electron phonon, superconductivity is everywhere. It has some dependence on density, but not very strong, because our theory right now, this theory that I'm showing is very simple. It does not include all the Van Hoff singularity. Maybe this question is better addressed when I show you more results, okay? So now I'm going to quickly go through how, this is rather simple stuff, but nobody thought about it before us. So graphene has all these values and all this chirality. So if you work out just the symmetry of the system, then you find that very easily you can have situations unconventional pairing given by phonons, because it can be inter-valley or intra-valley. And just from phonon, you can have singlet and triplet, and the leading order theory, they're in fact degenerate. Okay. And this is where somebody is asking about optical phonons. Optical phonons split these degenerates, okay, because they don't obey the same symmetry. Okay. So we pointed out something that, I mean, to me, it's almost looked trivial, but nobody knew before. A lot of our referees say you cannot get triplet, but you can. You have this, you have this depending on intra or inter-valley, you have this symmetry. So phonons can give you higher order superconductivity here. Okay. And I mean, I'm not going to go through it. It's not very germane for our thing. It's very simple, but you have worked on all the symmetries. And when you do the calculation, you include these symmetries. Okay. Now let me, move on and come to more serious calculations. Okay. So this is very recent work. That work was just the introduction, what we did in 2018 already, or 2018 to 2019. Then something radical happened. I hope all of you know. Andrea Young calls me one day and says, literally, that you may be right all along. I have now seen superconductivity in untwisted graphene, just regular graphene, but tri-layer graphene. Untwisted tri-layer graphene has seen superconductivity. So there is the mode physics, there is the enhancement of electron-electron interaction. And in fact, he kept it a secret. It was announced in a conference, in a Zoom conference, in honor of my late wife. And he announced it there, and Quantum Magazine wrote an article on this thing, and then the paper came out in Nature. That got us going, and I said, now we have to do a serious calculation, kind of calculation that CCQ does. None of this kind of theory calculation I do without details numerical thing. So we said we have to solve the gap equation with the actual band structure. So that's what I'm going to go through now, because now we're going to talk about, and we now did it for everything. Okay. So you all know what the gap, and then we estimated it. Now I'm showing you the results for this answers to your question, the density question. So this is first I'm showing you our detailed calculation, including the band structure, full band structure for twisted bilayer graphene. So this answered the question that Andy asked before, and you asked, how do things depend on density? So here what you're saying is just electron-phonon interaction, symmetry, and Van Hoff singularity interplay. Okay, so all these peaks going away, this all depends on the band structure. Okay, so this is a numerical calculation with the full band structure. Okay, but this is still twisted bilayer graphene. Now I'm going to talk about ABC tri-layer graphene. This is seminal work because it shows that this feeling people had, people have been talking, Holovic has been talking about it for a long time, that graphene may be superconducting. And people have seen telltale signs that many big, thick layers of graphene sometimes are superconducting things. There's something there. So this band structure is highly tunable by displacement field, by applying electric field. And they find there are a lot of symmetry breaking here. They find that near the Van Hoff singularity, there is a Stoner instability. There is a flavor polarization. Andrea is an expert in doing this thing. The spin polarized states are confirmed experimentally. Okay. So now the question is, but remember that I'm like totally set on electron phonon. Okay. So the question now is, if our theory cannot explain this, I would have written a paper saying, Occam's razor says it cannot be different mechanism. I cannot just change mechanism whenever I want. Okay. That's not theoretical physics. It could happen in life, but I don't like that. But the point is that there are Van Hoff singularities in tri-layer graphene. Band structure is not trivial. So there is large density of state. So maybe there is superconductivity. But there is ferromagnetic spin fluctuations also. So there could be spin fluctuation mediated superconductivity also. So which one wins? This question is not completely settled. Our paper came out, but I would not say. So this is the experimental data. I'm not going to go through the experimental data because I don't remember all the details. You have to trust Andrea that he did things right, and he found fragile superconductivity, but we see on the order of a Kelvin, at very specific points. So this is the dense Fermi surface. This is the calculated band structure Fermi surface, the density of states of tri-layer graphene. Okay, so you can see the Van Hoff singularities, but superconductivity happens near it, but not exactly as it is. And this is always was Pablo's point, that if it's the kind of electron flow mechanism we are talking about, superconductivity should be just around this. So we did a full calculation. I'll give away the story. What we find, no, it depends on some integrals. So superconductivity lasts over some range. It doesn't just disappear right beyond this. Okay, it's more stable than that. So we then do a calculation. It's a Yang-Zi Cho did a huge calculation doing band projection, and then using the BCS thing. I'll come to whether we do full Eliasberg or not. And so this is a linearized gap equation. I'm still talking about BCS. Then we solved it numerically. And what we find is that superconductivity, which is what is actually in the same regime where he's finding ferromagnetism. Okay. But if this means that it has to be phonons, if superconducting ferromagnetism are together. If superconductor is near ferromagnetic phase, then you have a lot of fluctuations, then paramagnets are possible. Okay. But then phonons may also be. So it's a complicated situation. Okay. Both are allowed. Which one it is, you have to do a question, and then you have to do a calculation, and you have to trust your calculation. Okay.
In the experiment, was the superconductivity suppressed under field?
Yeah.
It was suppressed under
Right.
field?
No, it was suppressed outside. It was more in the ferromagnetic regime. But in Barnard system is the opposite. Okay, so it's very confusing. Okay, I mean, here it's more phonon, but in Barnard is more spin fluctuations.
So one more question.
Yeah.
In graphene, the energy to reach the Van Hoven doping, it's just too the gauge.
No, that's for regular graphene.
That's what I'm asking.
Yeah, regular graphene is like caliber 15. Nobody has achieved it. No.
Now
No. People tried all this. They developed these techniques, electrolytic doping, but they could only go halfway. Okay. So this is the density of states. Now do a TC calculation. This is the the self-consistent BCS, and you can see that Van Hove is where the superconductivity peaks, but it doesn't disappear right away. So the argument that there is superconductivity far away from Van Hove, so it cannot be electron phonon, is just incorrect. And this depends a little bit on the grid. Young's is very careful, and it has converged but not completely. But I was happy publishing this. And so this is the result. This is electron phonon, and to what extent, this is the important thing here. To what extent it agrees with experiment? Experimentally, he finds 1.5 roughly. Okay, and we argued here that maybe mu star effect reduces slightly, but it's reasonable. So you can get TC1K in ABC trilayer graphene without Bore, and both in S and F are allowed. Okay. All right. So that's the story for there's just a lot of subtleties on it. He sees two different superconducting phases, SC1 and SC2, he calls them. And all of that are consistent, I'm showing, but I don't want to go into all these nitty-gritty details because there are two other systems I want to talk about. Barnard bilayer graphene and twisted trilayer graphene. Okay, because the subject is incredibly rich. Okay, and not everything is figured out by any means. Okay, we have just worked on electron phonon. And this Hubbard model thing excites me a lot, actually. Okay. So mu star would change number, but it's order 1 Kelvin. And so this is the superconducting 1. This is superconducting 2. This is the Stoner instability. So it's very dizzying. Yes, please.
So if I wanted to ask about superfluid stiffness of that,
which one are you talking about? Experiment or theory?
the theory.
Theory, yeah.
How many bands are playing here?
Oh, this is all in the ground state, in just one band.
So there's nothing interesting in superfluid stiffness.
No,
It's just
those bands are
BCS.
sufficiently far that it doesn't matter, right? Yeah.
Okay.
Okay, now so it's the agreement is, let's say, reasonable for such a complicated system. Okay. So a long time ago, we pointed out that that graphene, we did originally monolayer, but you can have multi-layer graphene, and you can calculate now, and d-rho-dt is 1 ohm per Kelvin, because again it's very small, because the electron phonon coupling is very weak, and we calculate for all these different materials. So we can now compare, and our prediction is, and this is a very important point, everybody should pay attention. Our prediction is that there should be a linear resistivity in this system, if it's phonons at some temperature. So the question immediately comes up. Our competitors who wanted to be electron-electron interaction, like Eresberg, very, very smart guy. Eresberg, Mike Zelator, two very, very smart guys. Okay, so they wrote a paper where they said, "Oh, look, our theory, they don't see linear resistivity in temperature." But the problem is Andrea only went up to 20 Kelvin. We have now done this theory very carefully, and resistivity should be linear around 50 Kelvin. It's a very big question, seeing linear resistivity with the correct slope that our electron phonon coupling is. So that is an open question. So he has promised you'll do the experiment. And then we calculated how electric field will modify things. As you know, electric field changes the band structure. we can calculate. So these are various gaps that electric field introduces, and eventually it should be suppressed. And some of these things, we did it because experimentalists did it, and it agrees with experiment. It's suppressed by the electric field. Okay? And we find that in the DP channel, this is our S and F channel. S and F are the superconducting 1 and superconducting 2. I don't remember which one is what. But our calculated TC in DP channels is basically 0. So those channels don't show up. This is a quantitative question. There is no fundamental reason why they don't show up. And any theory that does these things has to study the symmetry properties also. Okay, but that's not what the story ends. Then Andrea calls me 6 months after that. Now he seems to have seen a superconductor in Bernal bilayer graphene, which is the standard bilayer. Okay, not twisted. Okay. I mean, twisted bilayer graphene is a variant on this, but this is not twisted. Here, the most important thing you need to take home message: TC is very low. Look at TC. It's like order of 20 millikelvin. Before it was like 1 to 2 Kelvin. This is good because things should depend very strongly on band structure. Okay, and the band structure changes completely. These are band structures. Again, we have to calculate band structure. I've become a band theorist. I'm very happy. Okay, so I have persuaded my younger collaborators to become band theorists. That's the accurate statement. So this is band structure. It's very different from what it was before. We do the same. I'm summarizing the whole result here for you because I was not sure how I'll be doing with time, because there's one other thing I want to talk about. The calculation is very similar to the last one, but there is one difference here because TC is so low. Adding mu star in the last calculation changed our TC from 4 Kelvin to 2 Kelvin. Here, TC being this low, I insisted that we must include mu star effect, meaning the repulsive interaction effect. Now, first, there is a screening effect just coming from the gates. You have gates. So this is just the undergraduate image charge effect and you can derive this formula because there are many image charge. There are 2 gates. And immediately find the actual Coulomb interaction 1 over Q is suppressed by tangent hyperbolic Q over 2. All our calculations in bilayer graphene and in TMDs include, this is our Coulomb interaction because they're always gates. Okay? But this gives rise to very small mu star. So this doesn't explain experiment. You get, look at the TC we are getting here. TC we are getting is of the order of 1 Kelvin. And look at the experiment. TC is 40 millikelvin, right? So this is a huge difference. Okay. Only thing within our electron phonon interaction model, and maybe if one does Hubbard model type calculation that Andy was alluding to, that I certainly was not familiar with, maybe the 2 systems will have very different TC directly. Okay, but within our model, only thing I could think of is a mu star effect is very strong. So I said we have to include screening by the carriers themselves. And that we know how to do within ladder approximation. So we did that. We included that. And amazingly, TC did go down to almost the experimental values. Okay, I mean, after including mu star effect, we get results which are, not quite, but close to it. So, so this is what the story is now.
What's lambda here? Because there's no, DF is not suppressed. There's no magic angle.
No.
So what's lambda?
So the lambda is the lambda for regular graphene here. Yeah. Yeah. But remember the band structure, the Vanov singularity is what is giving the physics. Okay, so that's absolutely correct. Okay, yeah. So if you take an electron gas model or Dirac gas model, you're not going to get any superconductivity here. Okay. Now the last topic, which I want to talk about, because this is the electron-electron, I said phonons are not. So this is the not. These 2 groups, Santa Barbara, Columbia, and MIT compete. So Pablo came up with a paper. It's all in Nature, everything, where he saw superconductor with twisted trilayer graphene. More or less the same time these experiments are going. Twisted trilayer graphene. So here he finds the band structure is highly tunable by displacement field. And he claimed it's a spin triplet superconductivity electron-electron interaction. And why he knows that? Heck, he applies a field 8 Tesla, and this superconductivity, anything becomes stronger. Okay, so he calls me and says, can you explain this? Okay, first let me tell you, electron phonon interaction cannot explain this. We did the calculation, it just doesn't agree at all. Okay, so Yangzi was very depressed. I said, well, let's just do what Chibukov does in very nice theory. we'll assume that there are spin fluctuations since we know, and we are going to be what is called a spin fermion model. So this is not a microscopic model like I was telling about electron phonon interaction. Here is a more phenomenological model. We assume there are spin fluctuations that couple, and then we do the calculation. This is, has been done many, many times. And we, this is the phase diagram, experimental phase diagram. This is, the paper came out, I think, in 2021, in Nature. It's very complicated, but you can see superconductivity. And here the superconductivity is not peaked at the kind of singularity. So this is what, Pablo was triumphant. He said, it cannot be phonons, Shankar. He was like really, really happy. And so we did, we did the calculation. I'm going to show you the result. It's main idea of superconductivity spin triplet here. Normal statistic non-polarized, pairing from electron correlation. But we cannot do the kind of Hubbard model calculation or anything like that Andy was already. We really cannot do it. I'm not being modest. We do not have big enough computers. We don't have the skill. And so we did this, a phenomenology spin fermion model. And so here we, invoke there are some spin fluctuations, which is giving rise to superconductivity. And so, some kind of paramagnons. Since there is ferromagnetic state nearby, it's not an absurd thing, but it's a phenomenological model. And then you do the same calculation that I was telling you about with the spin triplet, with this ferromagnetic fluctuation. And we can take into account the symmetry, including spin fluctuation bosonic component easily, because we've already done it with phonons. And then we can identify which values are pairing, what should be the symmetries, P and F wave, because you can have intrasublattice, both are spin triplet. It's a bit dizzying. Then we mapped into a BCS model. Here the coupling is K independent, basically a Hubbard U-type coupling. And what we found here, the TC really is not that relevant because it's a phenomenological model. But what we found, this is the important thing: F wave pairing dominates over P wave. So that is true here also for phonons, and here is for spin fluctuation. So this was our bottom line, and then we can go further forward, and we can solve the problem exactly for if we just keep the F wave. Okay, and we did that. We can calculate all the free energy and find out how that will change in magnetic field. So we made a lot of predictions, and to my total amazement, this is not an important paper, but this got accepted in PRL because we kind of like. I think the important conclusion is this thing that even for this you get F wave pairing, and once you say F wave pairing, we can solve the problem exactly, and then we can give some idea about what would happen in the presence of small Zeeman field, and what the issue is. So, my timing is okay. So I will end. I have no summary. I'll end with a picture of, I didn't refer to anything. I didn't mention my co-authors except in the beginning. So if you are interested, these are all our superconductivity papers on graphene, okay? 10 papers. And right now what we are doing, a huge calculation going on, taking very long, but I'm determined. I made a vow that I'm never asking a student or a postdoc the status of a calculation, because when I ask that, they get very scared. They think I'm applying pressure on them. So 6 months ago, I was told it's almost ready. So what we are doing is this. We are doing the full resistivity calculation in all these systems with the full band structure. Okay, it's kind of the DMFT calculations you guys do, but for electron phonon interaction. Complete calculation. My real goal is to see whether we can push the low T linear coming from phonons all the way down to like 50 millikelvin. It goes down, but I don't think it goes down to 50 millikelvin. And this paper apparently is almost ready, and we should be posting it soon. And in fact, I'm much more interested in this resistivity than in superconductivity. And we'll see where it goes, because I want to be able to make a concrete statement. It is phonon or it is not phonon. Right now, as I said, I think it's 90% phonons, and I'm going to stop there. And thank you very much for your patience. Okay.
All right, thank you very much for this interesting and inspiring talk. So questions first from the audience in the room, and if there are people watching on the internet, write your questions in the Q&A or the chat, and I'll get to them.
Yeah, please.
Cyrus,
machines don't work. So I was just wondering, in the resistivity calculations, are those including all of the phonons?
No, just the resistivity calculation that's going on now is including all the phonons. But everything I showed you is just acoustic phonon.
Okay.
Okay.
Okay. And then I also wanted to ask, so you kind of flashed it, the different stackings of graphene
Right.
seem to have different power law dependencies on temperature. Like there was a T to the sixth and a T to the fourth.
Correct. That was the main point of that paper, that these power laws depend very much. But I should emphasize, those calculations are for very low doping because those are regular graphene. So Van Hoff singularity physics was not included there. So that's why we are doing that paper now with full Van Hoff physics. Okay. Some of those things have been seen at low doping, but I think much of this behavior will change. Now you're including the full Van Hoff physics. Okay.
So at low doping, the different power laws just come from different band structure, density of states.
Correct.
Okay.
Correct. Correct. And where the power laws change also come from that. Okay. Yeah.
Okay. Other questions? Shuin.
So, Shankar, maybe to follow up a little bit on cuprates.
Yes, please.
So what is the precise, you're saying that phonons shouldn't be ignored, possibly saying a stronger statement than that.
I am making a slightly stronger statement though. I'm saying, and I'll be very precise, I'm not being facetious. And I have had long discussion with somebody who is, well, I don't know if Jennifer knows him, somebody I respect enormously, Phil Allen at Stony Brook, who is an old friend, knows more about electron phonon interaction, risk and superconductivity than anybody else. And he always told me that I should do a serious calculation. Not all aspects of resistivity there can be explained by phonons, but it cannot be ruled out. And I said, I'm not insane. I'm not doing a calculation in high TC and claiming that it's phonons. The situation is this. It's a very complicated material. There's so many phonon modes. And what I learned from my material science friends is also very disordered, very homogeneous. So you may have phonons you don't even know about, local vibration and so on. So it's not easy to do it. But if you look at the raw numbers, first, this statement that is linear down to very low temperature is very misleading in two ways. One is linear down to very low temperature in very high magnetic field. Now, I'm not saying magnetic field will change the phonon structure very much and so on, but that's not the system we are talking about. Second, many experiments do not see linear down to very low temperature. People just quote the ones which do. I have looked at 500 resistivity papers, In some, it doesn't go to very low temperature. In some, it does. It's definitely not universal. What it is universal, that there is a regime, where it's linear. And electron phonon coupling that you need, if you just do a back of the envelope thing, it's just strong couplings, age of the strong coupling superconductivity. You need something like 1.5 to get the correct resistivity. What you cannot get is going down to below 10 Kelvin, because that if you convert into a free electron model, effective free electron model, then the cuprate electron density is of the order of 10 to the power 20 to the power 21 per cubic centimeter. Okay. So instead of 10 to the power 23, it's 10 to the power 21. So that's a factor of 100. And in K, if that's cube root, but it's still like a factor of 5 or 6. Okay. So that means if aluminum is linear down to 50K, a cuprate could be linear down to 5K just from the Fermi energy difference. So what I'm saying is that detailed realistic calculation is needed. And this kind of thing was only done in the early 90s. Phil Allen had a paper where he said it cannot be ruled out. Then Warren Pickett had a paper saying it can be ruled out. And then the interest moved away from all these things. All these phases came out and people haven't done it. So all I'm saying is that I don't want to do this calculation because, it's whoever does it, will never get a job. I mean, but it should be done. But there, I have this feeling, having done a lot of electron phonon calculation, that not everything can be explained by electron phonon. Now, Steve Kivelson tells me that he also thinks electron phonon may play a role. The real mystery is that you have many, many phonons. They're like, 5 different atoms in unit cell, okay? Why is the slope always the same? You think there should be little kinks. And so he thinks some kind of large N theory can resolve that. And I have not thought deeply about it. So all I'm saying is a precise statement. Electron phonon interaction has not been ruled out decisive there, okay, for resistivity. That's all I'm saying.
May I make a point about perhaps purity of samples? And,
yes.
If you look at the theoretical calculations, every linear resistivity, everything that gives you a linear regime, if you just extrapolate that to zero temperature, you get a strongly negative intercept.
Yes.
Right.
Yes.
And every measurement in both graphene and correlated materials does not have that negative intercept.
Correct.
The question is that simply a disorder offset that's pushing things up, or is there something else?
This is a very important question, but it could be connected to inhomogeneity also. That's, there is something we don't understand. This is, one, there are many reasons. This is one reason that I'm not comfortable saying it's just electron phonon. There are too many mysteries there. And when people just say linear down to low temperature, non-Fermi liquid, they're ignoring all what important one Andy just mentioned, that it doesn't go to zero, it's negative, okay? So that's why I'm not comfortable saying phonon, but I have not seen anything that decisively rules it out. I don't know if this answers your question, but this is all I can say, okay? I think Jennifer had a question first.
Sorry.
Yeah.
Yeah, I have a question. I think there was some experiment at Caltech where they put tungsten diselenide on top of TBG to induce spin-orbit coupling, and that made the superconducting dome extend over wider angles. So I was just wondering if the spin-orbit coupling plays any role or like proves any kind of mechanism, or if you view it as just suppressing some kind of ferromagnetic or
I don't know this experiment, but my answer right now would be just depressing the competing phases. I do not see spin-orbit coupling doing anything. I really think that just is suppressing the competing phase. I mean, I really think that if they can suppress the insulating phase, it's all a superconductor. When you look at the experiments as they evolve, it's just clear, it's effect of zeta, you look at it, it's just all blue, and there is a set of measures zero of brown, So I think I have to look at the paper and we'll think about it. But my quick answer to you is that they're suppressing. Yeah.
Okay, thanks.
Please.
I completely forgot about the negative intercept issue, because I used to be my pet peeve like quite a few years ago, and not being in the middle of this, I kind of feel like if the intercept is negative, that suggests to you, at least that suggested to me, that the low temperature expansion is just misleading.
Absolutely.
You shouldn't take it, and maybe you should do a high temperature expansion.
Yeah, you should.
So
Other possibility,
I have papers about that, but they never connected to experiments. So I'm just wondering, but when you see a negative intercept, what's your instinct?
This is of course a question I have faced this question several times. And first, my honest answer is that I do not know of any regular theory which will give that, but I can create that in homogeneity. So you have many different patches, you have percolation, and you could get any result you want doing that, okay? But I really, and a guy who grows samples for Rick Green, he once came to see me in my office and told me, these systems are really bad, completely non-uniform, and it's like, I can never, this percentage, because I wanted to know this percentage of different materials. He said it's no meaning because it's global stuff. But look, you have asked a very good question. I really do not have anything more to say than what Andy said. Andy, do you have a thought what may be happening, the negative intercept? What causes it?
Yeah, I mean, in the theoretical calculation, it's very simple. And you can see it if you do a high temperature expansion, the leading term is temperature, and then there's a negative correction.
Yeah.
Right. The point is that at low temperature, you have a power law with a high power, so it starts out at zero, and you have a power law with a high power of t, and then that folds over to something linear. And if you just think about how these things have to connect, that's more or less.
Yeah, but that is a trivial answer.
But the theory is trivial in that sense.
Yeah,
right?
yeah.
I mean,
but
that is the answer. The theory. The question is what's happening in the materials. Right? There's no theoretical issue.
No. I mean, if it's just a question of the extrapolation that way, that it is going like this, like that, and then you get a negative, that's, I hope it's something more profound, but maybe that's what it is. Something I did not even know. I mean, I knew, but I didn't realize that it's a universal mechanism. So it's almost always true, you're saying.
No. I'm not saying it's almost always true. I'm saying that within any of the standard electron phonon models, within the Migdal approximation, it's true.
Oh, yeah, that's absolutely true. That is absolutely true.
And I do think
that's absolutely true. Yeah.
The offset question is not trivial. There are a lot of cases in which you see linear resistance with approximately constant slope as you change something like doping. Yeah. And the magnitude changes, and you just don't get that out of electron.
I totally agree with you. This is what I said, that this slope thing, and you are pointing out even something more. But for me, if there are many phonon nodes and your temperature is changing by a factor of 10, more phonons should come in. And only way I can explain that by waving hands and say maybe one phonon has the most dominant coupling. But this is not an acceptable theory. One should do a calculation, And what you are saying, when you change doping, slope remains the same, but the magnitude changes. Very hard to see how that's going to come from electron. So there are mysteries. This is what I meant when I said I'm not comfortable saying it's electron phonon.
Okay, so if there.
I think this young man has a question.
Other questions? Yeah.
Just the first question, there are some experiments that are reporting that there might be a pseudogap phenomenology
In
twisted or
Byler.
yeah. So do you have any comments or
it's from
thoughts?
it's from MIT, right?
I can pull them up,
Yeah,
but I
yeah.
don't remember.
Yeah, well, I mean, the thing is that I think it's I cannot rule it out, but I think it's I think it's not good. I think it's really, I do not want twisted bilayer graphene to be a graphene copy of cuprates. Why Santil and Pablo want this, I do not understand. My goal is here that twisted bilayer graphene becomes like quantum Hall effect. We agree on what we understand, what we do not understand. I don't want to be like supercon high TC, where everybody has their own theory, nobody listens to anybody else. So I have not seen the pseudogap thing. I have heard it vaguely. I don't even understand what's meant by it. I think if I give a more serious answer, I think it's all an extrapolation question, something that we're talking about. You know, you look at some temperature, you see something, then you go and you can imagine that there is a gap. But if you send me the reference, I can give a more learned answer. Okay? I do not think that is anything. I think more or less the physics is understood now of twisted bilayer graphene. There is a lot of Chern insulator physics, fractional Chern insulator physics. There are many symmetries that are broken. They're all Mott physics with many other symmetries broken in a topological system. And then there is superconductivity, which I think is electron phonon interaction. But I am willing to be corrected. You know, I mean, I was very excited by what Andy said.
I mean, if there is, for argument's sake, a pseudogap, I understand that there is an interest in an exotic phase, but maybe couldn't that say that I have condensation of pairs in a VC picture from electron phonon coupling, not from exotic mechanism?
Yeah, you can certainly make a mechanism. It's a bit artificial, but you can do it. You can say, look, they're competing phases. So electron phonon interaction is trying to drive superconductivity, but it's competing with something. So it just forms the Bose condensate. The overall global coherence doesn't come in. You know, I can draw a picture like that, but I first want to make sure this phenomenon is universal. See, because of this twist angle disorder that, you know, world expert is sitting there, Jeff Pixley, experiments are like only generically ensemble average similar. You know, no two experiments see exactly the same phase diagram, and electron hole side are different. So one has to be very careful, okay? So, but what you say certainly can be cooked up if it's a universal phenomena. But I do not recall any details, but I vaguely recall that I have hard pseudogap, the word, okay? But I didn't pay attention to it.
I'll send it to you.
Yeah, please do. Yeah. I'm going to tell you what I think. Probably I will even contact the experimentalists first to find out what they are trying to say. Okay.
All right. So I think on that note, let us thank Sankar again.